You can write your own. There are some disadvantages. It does need lots and lots of training examples. But remember, that was an assumption that we made, not this lecture, the one before, that when we're doing discriminative training, we're assuming we've got lots of examples. Now, it's sometimes found to not work as well as some other methods. For example, support vector machines, which is something we're going to talk about in a little bit. And lately, there's been a lot of work on random forests, which I won't do in this class, but is sort of a even newer approach to doing that. And it's been particularly taken it a bit on the chin for many class problems, so not a binary classifier, etc. But it is still a pretty effective way of doing these things. All right, that concludes the boosting discussion and also the context of face detection. Like I said, it's rare that a single paper can influence a field so much like this one did, but it did. It not only influenced the field, it influenced the people sort of learning and thinking about the field. The representation, the classification method, and then the whole cascade, it just worked. It just worked really, really well. And as I said, unlike SVM methods, which we'll learn about next time, you can actually just write the code yourself, both boosting and random forests. By the way, random forests are sort of related because it's this idea of adding this consensus of weak learners. So for those of you who want to think about random forests because you know about them, you can think about them in that context. These boosting algorithms, these consensus algorithms, are just much simpler to implement yourself, and therefore they sort of become fun to play with. Next time we'll talk about support vector machines, which are not fun to implement, but just work really, really well. All right, welcome back to computer vision. If you remember last time, we started talking about discriminative classifiers. So we first did generative, then we did discriminative. And the idea of discriminative classification or recognition is that instead of worrying about modeling our classes, we're going to learn a boundary. We're going to learn a surface in some feature space that divides our classes. And we've talked about two simple methods, well, actually one simple method, nearest neighbor, a much more interesting method of boosting last time, where we were talking about the Viola-Jones face detector, which used boosting. But today we're going to talk about support vector machines. Support vector machines became a very significant method of doing classification, and especially as applied to computer vision. It really, and today, and still today, is fundamental. So in order to learn about support vector machines, we have to talk about what are called linear classifiers. And linear classifiers are exactly what you might think. So here I have some data points. I got blue ones and pink ones. And the idea would be, what if we just wanted to find a linear separator that separated things? Well, in this particular case, we could do that, no problem. So it would be something like that. Ta-da! There's our linear classifier. And you know, what we'd like to do is to talk about finding these kinds of things automatically. And then the whole point of support vector machines is to do these in well, what you'll see is some higher dimensional spaces, which will give us some very effective classification, some powerful classification machinery. So let's talk a little bit about lines. So here's just lines in regular 2D space. So here's an equation of our line, and this is the normalized equation, and we used to write ax plus by plus c equals 0 when we did a bunch of things. And I'm not doing that here because in SVM land, where it's derived, b has a particular value. It talks about it's written in a particular way. So I wrote it as px plus qy plus b equals 0. And really what I mean to say is that we're going to let some w here be pq, and pretty soon those will go away, and we'll only talk about w. Let w be pq, and if we have some point x, which will be sort of little x, little y, then the line px plus qy plus b, that's the same thing as this line w dot x plus b equals 0, right? And w here, this vector here, that's going to be in this direction there, okay? One thing that should be clear from this, right, I could scale w and b and it'll still be 0, right? Multiply both of them by 3 and I get the same value, all right? Now, if I have some point, x0, y0, I might want to talk about the distance, cap d, of that point to the line, okay? So here we have our point, and then there's this question of what that distance d is, all right? Well, given the equation of the line, we can express that distance in just the following way. It's just essentially find the dot product of that on w subtract off or think of that as being connected to B. Whatever that value is, that's how far off the line it is. And you then have to normalize, because we're talking about distance, by the magnitude of P and Q. So that's why it's divided by the square root of P squared plus Q squared. And that can be just written like this. Okay, so it's just W transpose X plus B, the line equation up there, divided by the magnitude of W. Okay, so that's the distance D. If we want to build a linear classifier, so we want to find some function to separate the positive and negative values. And the idea is that we want a line x dot w plus b such that if the xi is positive, so if that value is greater than 0, we're going to call it a positive. So that's here. So if it's greater than 0, we'll call it positive. And if it's less than 0, we'll call it negative. But let's take a look at these data. So here's a line that separates the blues from the pinks. That's a good line. Isn't that a good line? Sure, it's a great line. But here's another line, all right? And here's another line. And here's another line. And all of these lines separate the blues from the pinks. So the question is, of course, which line is best? All right? And support vector machines are a particular take on how to decide which line is best, and then we'll go to hyperplanes and higher dimensions, etc. But it's basically having to do with which classifying separator is best. So support vector machines, SVMs, are really this idea of the optimal or the best possible separating line, or in higher dimensions, plane. And the way we do that is, so you see this line here, this line is drawn down the middle there. Well, sort of down the middle. Okay. Well, great. Now it's a ribbon. Okay, fine. That line down the middle. And the dotted lines here, right, this is sort of the closest distance of the points. So those two lines are drawn such that this line is the closest blue, here's the closest red, and this separator line is down the middle. The idea of the support vector machines is that we want to maximize this distance between those dotted lines. And that distance, that's called the margin. Okay, it's written in green here. That's the margin between the positive and negative training examples, right? So here, so it's from here to there. Okay? And the idea is to try to find the line that gives us the best margin. All right, so to do that is just a little bit of math. It's not a horrible amount of math. It's just sort of pretty straightforward. So here's our line, and let's set our line to be wx plus b equals 0, and that's going to go down the middle of the line. I'm sorry, down the middle of that's going to be our separating boundary. Now, what we can do is we can say the lines that are the margin lines, the ones that hit the nearest points, we can say that the value on one side is w dot x plus b equals -1, and on the other side, w dot x plus b equals 1. Now you might ask, how come I can set them equal to 1?
How come I can set them equal to 1?
Megan's asleep over there, but she got to it eventually. Well, remember I could scale w and b, right, and still have wx plus b equals 0. So what I can do is I can scale them up to make it so that those distances are 1. What we want is, we're going to define a little auxiliary variable called y corresponding to the x's. And the idea is that when I have a positive x, we're going to define y to be +1. And when we have a negative x, and what I mean positive is a positive example and a negative example. You know, this is a baseball, this is not a baseball. All right. So when y equals -1, we want x dot w plus b to be less than -1. So that's a way of saying that, you know, we want all the positives to lie over here, and we want all the negatives to lie over there. Okay? Notice that on this drawing, there were a couple of special points. Okay? Now, in today's age, we like to tell points, all points are special. But in reality, just like real life, only some of us points are special. Okay? In particular, this point is special, this point is special, and this point is special because they define our margin. All these other points out here, they don't impact our margin, right? And this is part of why discriminative classification is sort of better, not sort of, is in some sense better than generative. We don't actually have to worry about representing all these points out there. We're just representing the boundary. But getting back to what we're saying, that we have these three special points that define what our margin is. And those are referred to as our support vectors. These are vectors, right? They're points in our feature space, or you can think of that as a vector. And these are called support vectors because these are the ones that sort of define for us that best separating plane. So those are support vectors, okay? So at our support vectors, x dot w plus b actually equals 1, right? Okay. And the distance between those lines, that's going to be referred to as our margin. So we can compute the size of m as a function of these values, right? So we have the same equation we had before. The distance between the point and the line, x dot w plus b normalized by w. Okay, that's the distance between a point and a line. Well, so for support vectors, w dot x plus b is just either plus 1 or minus 1. Okay, it's plus 1 on one side, minus 1 on the other side, divided by the magnitude of w. So that means that m is just, 1 minus negative 1 over w because of that value, right? And so it's just 2 over w. Okay, so the margin m is just 2 over w. What we need to do is we want to find w that does what? We want to maximize the margin. So we write that like this, all right? So just as we said before, we're going to maximize 2 divided by the magnitude of w. Subject to the constraint, we want to correctly classify all the points, right? So for the positive x's, where y is plus 1, we want x dot w plus b to be greater than or equal to 1. And if xi is negative, we want x dot w plus b to be less than negative 1. All right. So this is a standard, what's called a quadratic optimization problem. We want to minimize this term that's over here, okay? Because if you minimize the square of w, then that's going to maximize 2 over the norm of w. Subject to a constraint, right? Here's our constraints. You'll notice that what we did is by multiplying by the yi, we can say that this thing is always greater than or equal to 1, right? Because yi flips the sign, because yi is positive when it's a positive example, and yi is negative when it's a negative example. So multiplying it through keeps that constraint always greater than or equal to 1. The solution to this, and I'm not going to go through the solution, it's sort of a standard quadratic optimization and some Lagrange multipliers and things like that, but what matters is the form of the solution, not how we got there. It's just the linear sum for w of some weights times, and it's the yi times xi. So remember, yi sort of flips the sign. All right? And the xi's that you use are the support vectors, and the alpha i's are these learned weights. And another way of thinking about it is that the weights, you can think of that I have alpha i's for all of the xi's, but they're only non-zero for the support vectors. Okay, so when I solve this, I end up with a whole bunch of alpha i's, most of which are 0, but the alpha i's for the support vectors are non-zero. Okay, well then I can just sort of substitute in. We have this equation that remember, for any support vector, w transpose x plus b is equal to positive 1 or negative 1, depending upon whether it's positive or negative example. So that can be written like this. Remember, the yi's are plus 1 or minus 1, depending upon the example. So I can write, just substitute in for w. Okay, so I substitute in for both b and for w. Given this, we can now create a classification function. So remember, what we were doing is we were drawing a line, wx plus b equals 0. Everything on one side of the line we were going to call positive. Everything on the other side we were going to call negative. Right? Our support vectors are out here where that function equals 1, but if something's on the inside, if it's greater than 0, we'll call it positive. Less than 0, we'll call it negative. So I'm going to build a classification function, which is right what it says here. It says, okay, I'm going to just take the sign of w dot x plus b. Greater than 0, I'll call it positive. Less than 0, I'll call it negative. I substitute in for w this expression here, okay, and take that sign. And if this function f of x is less than 0, I'll call it negative. And if it's greater than 0, I'll call it positive. Okay? So this all depends on you being able to solve for those alphas, and I'll tell you the support vector machinery will do that. And realize by solving for the alphas, by finding some non-zero alphas, that's selecting your support vectors. Okay? A critical element of this equation is that it only depends on this dot product. Okay? It's highlighted here in red. I'll highlight it in red again. The only thing I need to know is the dot